everybody, it's Tyler here at Kettering 1, checking in with Hall of Fame Team 27, Team Rush. Team Rush, every single year, just really elevates the bar, built some phenomenal robots. Hopefully you saw the reveal video where they got a lot of great stuff going on. Had a great day here today at Kettering 1 in day number 1, and we're going to take a look at their robot. Last year won MSC, and really just rocking it again here at Kettering. You got to take a look. This articulating claw is really one of the big stars of the show. They got a great deep climb as well, too. We'll dive in more into their elevator, how their whole chassis comes together, a little more on their machine learning, PhotonVision, a lot more to talk about coming up here on Behind the Bumpers. Amir, we got a lot to talk about and break down this robot here. Talk to me about your drivetrain, and we're going to be going into your chassis with that awesome climb you have as well.
Yeah, so we're using swerve drive this year, and our robot is 28 by 28, and we're using Mark IV eyes and Kraken X44s for our steering. And if we want to walk over here to our climb mechanism, our objectives for a climb this year were to have quick and deep climb so we can get that climb RP. And we originally wanted to go with a donut method with a hole inside the middle, but we wanted to save space for our chassis electronics. So we decided to create a new mechanism, and we have active wheels on our climb that will grab onto the cage, and then we have a passive latch that will allow us to stay onto the cage.
Can we see how that climb actually deploys? And
Yeah.
take a look at it? And can you kind of walk me through how that process all works?
Yeah. So the operator will deploy the climb up, and then they'll deploy the climb down once we latch onto the cage. And then we're up.
How long does it take you typically to line up and get that climb going?
I'd say about 10 seconds.
So overall, it's been working out great for that. Let's keep rolling on this robot here. Pass over to Ryan and talk about the elevator and the carriage with this. This whole structure is just, it's every single year. It's always gorgeous with Rush as well too. But break down for me how this all came together.
Yeah, so I'm going to start off with the elevator. Our elevator this year is a 2-stage continuous belt-driven elevator with about a ratio of 2 to 1. For our elevator, the max height is about 72 inches, and we have a theoretical travel time of about half a second from top to bottom. A little bit more into our carriage, we have a articulated wrist, as you can see here, just miter gears for rotation. That's about 50 to 1, and then we have a pivot that is about 150 to 1. This travels all the way up and down, and then it, of course, attaches to our claw with the hub. And for our structure, we added this structure later on. It was integrated pretty well with our robot. It both holds our sponsor panels, and guards against coral, along with holding up our elevator and just general support structure.
So in design process on this here, like how did this actually all come together? Or what was the initial concept? And did you have any other concepts in terms of what the superstructure would look like?
So our initial design was just an elevator on the robot, but later on we added the structure. As you can see here, these brackets were added later on to the 2x1s. And you can see here, this was also added later on to the swerve drive and the climber as well. For how we came to this was that we found out after we had mounted our elevator, the robot, that was a little shaky, so we wanted to better support it.
Level 4, level 3, level 2. And how are you determining like where your stops are in terms of all that?
So all of our stops are, I would say, mainly controlled through trial and error on testing with the Reef with our programming. We also have some that help. What also helps us is our Ardu cam, which has reef detection.
And I know we'll be going to programming a little bit later as well too. Let's pass over to Aubrey, talk more about the claw. I mean, this thing is sick, by the way. This is so cool on here. So talk to me about how this comes down. And I got to ask you as well too, as part of the drive team, like what is it like trying to operate this machine overall?
Well, I think it's pretty awesome. I mean, this claw is very diverse in its functions. It can do a lot of cool things like descoring the algae on the branches and scoring the coral on the branches. It's a lot of fun to play with all of its functions.
So this design on here, when you were looking at like different options for what to come up with, were there any other designs you had prior?
Yeah, before we weren't going to have this polycarb tube here to allow the claw to pass through the bumpers, but we decided adding the tube would give it more reach for ground pickup and scoring, and it was just a better option.
So let's see the claw articulate a bit, because I think this is really interesting. When I'm watching you score on the field with this, sometimes like I see the claw twist one way versus the other. What determines like which way the claw is twisting?
Well, our operator can control whether the claw twists or not, and usually the decision is made whether it twists if the coral is too far on one side and if it would make it too difficult to score it. So
So in terms of like ground pickup versus picking up from the station, how do you do that in a match? Like, what is the priority for you?
Well, if there's a coral close to us, then we can decide that we'll pick up that one to shorten the distance we have to travel from the human player station to the reef, and yeah.
So there's a lot of great electronics that go into this robot here. We were talking earlier, running 2 CAN buses with this as well too. So break down some of this. I mean, this overall packaging on this is just gorgeous, by the way. So walk me through just some of the things that go into this.
Yeah, absolutely. So to start, I'm going to start with how our wires were laid out this year. Normally we use an inverted belly pan, which is we put everything on the bottom of our belly pan so that the top here isn't that much of a mess. We can get into it whenever we need to. This year, due to the need to raise so many wires up, we decided to mount our PDH on top. So we have our PDH on top of our electronics, or on top of our belly pan, and then all of our electronics are on the bottom. This made it easier to attach to our elevator and to our claw. So you can see here we actually used an E-chain this year to protect our wires. It's the first time in 5-6 years we've done that. About our CAN buses, we actually are running 2 CAN buses this year. One for all of the cross-throat electronics we have, so all of our Krakens, all of our our CAN ranges up there, the time of flight sensors we haven't used. So those were fun to learn how to use. But our second CAN bus is actually for our Neos. Our climber is running on Neos because we had specific 7-to-1 gearboxes we wanted to use, and the Neos fit perfectly into them. So we decided to use Neos for our climber. That made us have to wire up a completely different CAN bus and connect it to the Robo Rio instead of to our Carnivore.
So something I'll ask you, when you have all this just gorgeousness that goes into this, like, what is something maybe you would recommend the teams who are like looking to up their game in terms of packaging for all this?
In terms of packaging, we'd recommend making each individual component as easy to detach and reattach as possible. Something that we do is we solder all of our wires on the bottom, but towards our climber here, you can see we have Wagos and other connectors to connect to it. That makes it a lot easier for us to detach whenever something breaks or a wire may fail. We can always detach them easier than having to go through and cut a wire and resolder. And that allows us to get our part off, make sure it's working, replace parts if needed, and put it back on in a quick fashion without having to take 10, 20 minutes. And we can get back on the field pretty fast.
So Sam, anything else to wrap up with in terms of that area? And I know we got a lot in terms of software and programming, machine learning stuff you want to dive into too. Tell me more about it.
Sure thing. We'll start with our Orange Pi. This is the first year we're doing an Orange Pi coprocessor on the robot. It's located right here on top of our network switch. That's connected to just one camera for now, which can be found up on the top of our elevator on the static stage. This camera, unlike a lot of teams who are using it for object detection, we actually use it to detect the poles on the reef. Rather than using solely April tags to line up with the faces of the reef, we have a hybrid lineups system where we drive close enough to the scoring location with April tags, and then we switch over to a combination of our sonar, as we call our CAN range sensors, for both angle and depth, and our camera up here for just the side-to-side alignment with the reef poles.
Overall, this is a phenomenal machine for what this is coming into, and it's been really exciting to watch Rush play year in and year out. So thank you for being such a great inspiration to the entire FIRST community. That there's so much I think FRC teams can take and learn from this, so hopefully you had an opportunity to do that as well. Team Rush, good luck here, of course, and looking to go back-to-back at MSC, and hopefully even further at Worlds as well, too. Good luck the rest of the way.
Thank you.